Good morning, everyone. I am Karan Singla, and today I'll be presenting on the topic rotational rheometer. Now, before moving into what is rotational rheometer and how it works, we have to understand what is rheology. Now, rheology comes from the Greek word rheo, which means flow. In simple terms, rheology is the study of how materials deform and deform and flow when a force is applied. This science is fundamental across various industries. For instance, in polymers, rheology helps optimize processing and performance, while in the food industry, it helps in processing and optimizing the right texture and mouthfeel. And in pharmaceuticals, it helps with the formulation, stability, and effectiveness. Now, coming on to what is rotational rheometer. Rotational rheometer is an instrument used to measure material viscosity and flow behavior by applying a controlled rotational force or torque and measuring the material's resistance to flow. Now, we have to understand how the rotational rheometer works. The working principle of rotational rheometer is quite straightforward. In this device, a sample is placed between the two surfaces, one that rotates and the other one which does not rotate and remains stationary. As the sample is sheared or deformed between these surfaces, the rheometer measures the material's resistance, capturing data that help determine its viscosity. The setup's geometry significantly affects the data. Different configurations are used based on the properties of the sample, which leads us to the types of geometries in rotational rheometers. Talking about the different types of geometries in the rotational rheometer, the first one being the cone and a plate. In this type of geometry, the liquid is shared between the upper rotating cone and a lower fixed plate. In this combination, the liquid is sheared evenly into completely horizontal fluid layers. Now, average geometry has its pros and cons. For this type of geometry, the pro is that it requires minimal space volume and allows for precise shear rate measurement. For this geometry, the con is that it is not ideal for the liquids that has particles in it. Moving on to the second type of geometry, it is plate and a plate geometry. The liquid is shared between the upper rotating plate and lower fixed plate. The liquid shared also in this combination, the liquid is also shared into horizontal layers, but not as evenly as that of the cone and the plate. For this geometry, the pro is that it can handle the samples with particles in it. But the con is that the varying shear rate can require software compensation, and evaporation can affect results. Now, moving on to the third type of geometry, which is a cup and a bob geometry, the liquid is shared between the central rotating bob and the fixed cup. In this, the layers become concentric cylinders such that the shear stress acts on the large surface area compared to the cone plate geometry. For this, the pro is that it is ideal for thin liquids and it minimizes evaporation issues. For this, that the co for this type of geometry, the con is that this setup requires a larger sample volume and cleaning can be more labor intensive. Now, moving on to the key parameters that are required in determining the results of rotational rheometer. The first one is the viscosity measurement. Viscosity is the measure of a fluid's resistance to flow. In a rotational rheometer, we can measure both dynamic viscosity, which changes under varying shear rates, and a steady state viscosity, which remains constant as a fixed shear rate. The second parameter is shear stress and shear rate. In shear stress refers to the force applied per unit area, while the shear rate describes how quickly the material deforms. Together, they help us analyze viscosity behavior under different conditions. The third parameter being a yield stress it is the minimum stress required to initiate flow in a material. For example, in products like creams or paints, yield stress helps the product maintain its shape until it's applied. The fourth parameter is elastic and viscous moduli. The elastic modulus, that is G dash, represents the material's solid-like behavior, while the viscous modulus G double dash represents the liquid-like behavior. These values are especially helpful for studying viscoelastic materials like gels and pastries. Now, talking about the tests that are performed from the data that is gathered from the rotational geometry. The first test is the plotting of the flow curves. By plotting viscosity against shear rate, we can easily classify materials. For example, a Newtonian fluid, as you can see in the diagram, a Newtonian fluid like water has a constant viscosity, while the shear thinning fluids like ketchup decreases in viscosity with higher shear rates, and the shear thickening fluids increases in viscosity with the shear as the shear rate increases. The second test being the oscillatory test. These tests are essential for studying the viscoelasticity of materials where both liquid and solid properties are present. A sinusoidal shear stress is applied, and the phase difference indicates whether the material behaves more like a solid or a liquid. The third test being is the creep and recovery test. A creep test applies a constant stress to observe material flow over time, while a recovery test measures the material's ability to return to its original form once the stress is removed. This protocol is crucial for evaluating long-term stability. The fourth test being the temperature ramp test. Here we measure how viscosity or elastic modulus changes as the temperature fluctuates. This test is particularly useful for materials that are sensitive to temperature, ensuring that products perform reliably under real-world conditions. Talking about the applications of the rotational geometry in lithium-ion battery manufacturing, they are used to ensure slurry quality, critical for battery performance. In food processing, these rheometers help control shear rates, which impact texture. In polymer production, they allow for quality control, especially during processes like extrusion or molding. And in pharmaceuticals, they evaluate formulations such as creams or gels for stability and application ease. Now, thank you.